Hi, this video is about what people mean when they say momentum is conserved. Now, I want to start with an example involving two ping pong balls on a table. So here are the two ping pong balls. I'm going to put one at rest right here on the table, and I'm going to send the other one straight into it. All right, so observe what happens to the motion. I'll do it one more time here. Oh, whoops. There we go. I'm also going to try to send them into each other and see what happens there. So they are moving towards each other and they collide. Watch what happens to their motion. That's not. I'm trying to get it straight so they bounce straight back off each other. There we go. That's pretty good. What we just observed is that momentum can be passed on from one object to another. To illustrate what I mean by that, I've drawn a picture of a collision of two balls before the collision, during the collision, and after the collision. And I've drawn the red ball here moving towards the green ball, which is at rest. And then after the collision, both balls are moving to the right. During this collision part, both of the balls are experiencing a force. They're both accelerating in some way. The red ball is slowing down and the green ball is speeding up. So they're both experiencing a force. And because of Newton's third law, we can say that these two forces are equal and opposite. So the force that's acting on the red ball is equal to the force that's acting on the green ball, but they're in opposite directions. So using algebra, if we multiply both of these forces by the time that they're colliding with each other, the time that those forces are acting, then the product of force and time is known as impulse, this quantity in physics of force multiplied by time. And so we're essentially saying that the impulse on the red ball is equal to the impulse on the green ball, but opposite direction. And what we know about impulse is that the impulse on an object is equal to that object's change in momentum. So the change in momentum of the red ball is equal to the change in momentum of the green ball. Whatever momentum loss you have from the red ball, it's gained by the green ball and vice versa. So to illustrate this, let's just add some numbers here. I'll make up some measurements here. Let's say that the red ball is moving with a momentum of 5 kilograms times meters per second. And let's say they collide with each other here, and afterwards the green ball is moving with a momentum of 3 kilograms times meters per second. So originally the green ball wasn't moving at all. Now it's gained 3 kilogram times meters per second of momentum. So it's a +3 over here. That must mean that the red ball has lost 3 kilograms times meters per second. So there's a loss of momentum from the red ball, but that loss of momentum for the red is gained by the green. So that would mean if the red ball has lost 3, then it's going to be moving with a new momentum of 2 kilograms times meters per second. So whatever momentum you lose, it's gained by the other ball. In other words, momentum can be passed on from one object to another. Let's look at some examples, still involving two balls colliding with each other. So this first example at the top here, we have one ball moving at 5 Newton seconds. A Newton second is just another unit for momentum and is shorter to write and say. So I decided to use that unit instead of kilograms times meters per second. So we have 5 and 0, and after the collision, we have 0 and 5. So if you look at the change in momentum of the red ball, it's gone from 5 to 0, so that's a change of -5. And the green ball has gone from 0 to +5, so that's a change in momentum of +5 Newton seconds. So you can see these two are equal and opposite. We have -5 and +5. Similarly, we have +4 and +1. They're both moving to the right, but the red ball collides with the green ball, and after the collision, the red ball has 2 Newton seconds of momentum, whereas the green ball has 3. If you analyze it again and look at the change in the red ball's momentum, it's gone from 4 to 2. So it's lost 2 Newton seconds of momentum. The green ball, on the other hand, has gained 2 Newton seconds of momentum. All right, this last example, what if you threw the balls together like I did there? What if they collide with each other in this way? Let's say we have 10 Newton seconds to the right, that's positive, and then 5 Newton seconds to the left for the green ball, that's negative. So they collide with each other and they end up going in opposite directions. They bounce off each other. And the red ball moves with 5 Newton seconds to the left, and the green ball goes 10 Newton seconds to the right. What's the change here in the red ball's momentum? It goes from a positive 10 to a negative 5. So that's a change of negative 15 Newton seconds. And the green ball goes from negative 5 Newton seconds to positive 10. And so that's a gain of 15 Newton seconds of momentum. So if you look at this, it's always equal but opposite changes in momentum for any two colliding balls here. If you look closer at these situations and you add the momenta before and after the collisions, the total momentum stays constant. And so this is actually a more useful way to sort of analyze these situations. If we added these two together at the beginning, 5 plus 0, we start with 5 Newton seconds, and we end with 0 plus 5, 5 Newton seconds. Same thing down here, 4 plus 1, we start with 5, and 2 plus 3, we end with 5. So the total momentum is staying. Now, if we add the positive and the negative here, positive 10 plus negative 5, that's still a positive 5 Newton seconds. And negative 5 plus 10, that's positive 5 Newton seconds. So in each of these situations, the total momentum of the two balls added together is constant. It's at 5 before and after the collision. And so this is a more useful way to keep track of how much momentum the system has as a whole, the system being the two balls added together. So let's talk about this and come up with some conclusions here. So the total momentum of a system of objects remains constant as long as everything within the system is free from any external forces that may influence momentum. So free from things like friction that would slow an object down. A system is a collection of two or more objects. We use that word system to talk about the two balls together, or however many objects you have, we collectively call them our system. And when a system is free from any external forces like friction or heat being generated or any kind of loss of momentum, if it's free from any of those external forces, we say that the system is isolated. Isolated being completely separate and removed from any other forces, just focusing in on the two balls. So another way of saying that the momentum remains constant, as we set up here, is to say that the momentum is conserved. Being conserved means you're not losing it, you don't lose any of it, and it doesn't get used up. The momentum is not lost, the momentum is not used up at all. And so to wrap all of this up into one concise sentence, the momentum of any isolated system is always conserved. The momentum of an isolated system is always conserved. So I want to give you an analogy to end with to help drive this home. And I like to use the analogy of money and an app to transfer some money. So let's say that we have two friends here, Jim and Bob. Jim has $25 and Bob has $10. Let's say that Jim pays Bob $20 through an app. Okay, so then Jim goes down to $5, Bob goes up to $30. As long as the app doesn't charge a fee, then none of the money is lost. We can say that the money is conserved between the two of them. The total before was $35, 25 plus 10 is 35, and the total after is still $35. And so none of the money gets lost or used up, and so the money is conserved. However, If there is a $1 transaction fee on the app, then the money is not conserved due to an external force, in this case, the app, taking some of the money. So money can be, conserved as long as there's nothing else taking the money away or adding money. As long as the system is isolated from any external forces like transaction fees, then the money can be conserved. So on the other hand, a red ball has 25 kilogram meters per second of momentum, and a green ball has 10 kilogram meters per second of momentum. Same numbers as before over here. We say the red ball transfers 20 units of momentum to the green ball. So we now have 5 and 30. And just as before, as long as the interaction is free from any external forces, then none of the momentum is lost. And so we say that the momentum is conserved. However, often there is some loss of momentum. There's often some kind of force involved, like friction or heat being generated in the collision. And so often we do lose a little bit of that momentum, and we end up having momentum not being conserved. Momentum is taken from the system and given to the ground or air particles in the heat that's generated. And so oftentimes momentum is not truly conserved in the situation, but we try to keep things simple in physics. We try to analyze things as simply as possible, and we can often neglect or ignore these small losses of momentum due to friction or heat. That's all I've got for you in this video. Remember, how you do anything is how you do everything.